Hi everyone, this is Zhenfen. Today I'm going to introduce our recent work on PADCLIP. We will talk about how we can use CLIP for the unsupervised domain adaptation tasks. This is a joint work between UC Davis and Amazon. Yeah, first I want to give a brief introduction of what unsupervised domain adaptation is. So basically, for the UDA tasks, we will train a model on the label source domain, and then we will test it on the target domain. But for the target domain, we do not have any labels. So here is one example. For example, if we have the source domain is art, then for the other three domains, we will not have any labels during the training process. And for this work, we will talk about how we use CLIP for the UDA. So the first question is, why do we want to use CLIP for the UDA tasks? So if we take a deeper look at the domain adaptation problems, like a photo, like a painting or a painting of dog or a clip art of a dog. So if we wanted to use clip and use the clip's loss during the training process, and if we want to minimize the loss, then the domain information, the class information can be automatically disentangled. And the second reason is that clip itself is pre-trained on 400 million images, and we think this is a good source to bridge the domain gap. However, if we directly fine-tune CLIP, then we will have a very severe forgetting issue. So here's one example that if we do full model fine-tuning, then we can see there is a big drop of the performance because the CLIP may lose the pre-trained knowledge. Therefore, in this work, we present three components to leverage CLIP for the UD tasks. The first thing is that we want to preserve the original knowledge of CLIP. Then we want to talk about how we can exploit or fuse the new knowledge on the source domain. Lastly, we will leverage unlabeled data by using pseudo-labeling. Here is one of the overview of our proposed method. So basically, for the source domain, we have the label. So for the label, we will convert it into a prompt that can be used for CLIP training or fine-tuning process. And then we will fine-tune the vision encoder here. On the other hand, we propose a measurement to measure the performance of the learning status. On the other hand, for the target domain, as we do not have any label, so we will have weak and strong augmentations and generate pseudo labels. So for example, here, for the weakly augmented images, we will have a pseudo label, and then we propose a consistency loss on the target domain. Yeah, so here is the details of the pseudo labeling. So basically, we have a threshold over here, and then we can generate the 100 pseudo label. However, pseudo labels can be biased because the distribution of the target domain may be totally different from the distribution in the source domain. Therefore, we propose another module, which is adaptive causal inference. With adaptive causal inference, we can debias the pseudo labels and generate unbiased predictions during the training process. And then lastly, we can see here is our results. We can outperform the previous methodologies, especially on domain net. We get over 18% improvement. Yeah, so in conclusion, we think CLIP itself is naturally beneficial to UDA tasks. And if we can preserve the pre-trained knowledge and leverage the new knowledge, then CLIP can be useful for the UDA task. However, it is time-consuming to do full model fine-tuning for multiple domains. So in the future work, we also aim to study parameter-efficient adaptations, and we want to study the trade-off between learning capability and the parameter scale. Yeah, so this is our work. Thank you for your listening.